All right, so now we're going to talk about this idea of excision. And excision is just based on the observation that in relative homology, what matters is not the set k or k0. What matters is the difference between k and k0. Okay, so it's quite possible then to have two different pairs of spaces which have the same relative homology, so long as the difference between those two spaces or those pairs are the same. Okay, so by sort of construction, right, in relative homology, the pair k comma k0 doesn't really matter. What matters is k excluding k0. Okay. So the basic idea then is that you could have a different pair, say L comma L0, where you've basically, which are contained, it's like, if you will, it's like in k comma k0. And you can do this so long as, the difference between the set L and L0 is the same as the difference between the set k and k0. All right, so we can remove simplices from both complexes so long as the difference remains the same without affecting the relative homology. Okay, so let me state formally this excision theorem, and I'm going to write it here so that I have a little bit of space to show you the proof. So the excision theorem says the following. So let's say that we have k0 is contained in k, L0 is contained in L, right? Be pairs of simplicial complexes. That have the following property, that L is contained in k, and L excluding L0 is equal to k excluding sort of k0. Okay. Then the claim is that they have isomorphic relative homology groups. Okay, which is to say that HP k comma k0 is isomorphic to HP L comma L0, and this is true for all dimensions P. Okay, so so we're going to try to prove this instead of using standard algebraic techniques. We're going to prove this using the Smith normal form, it's like which we had computed before. And in particular, we're going to discuss, well, what does this, what even the boundary it's like map looks like in the reduced sense. But when sort of embedded, if you will, it's like in K and L respectively. Okay, so we'll sort of use the Smith normal form instead. To prove this. And so the first thing we do is that we have to order, we're going to order the simplices. So we'll order the simplices in K, right? So that the simplices in K0 appear for those in k excluding k0. Okay. All right. So let's now look at how that boundary matrix looks like. Okay. All right. So this thing here is going to be the rank of CP K0 in dimension. This is going to be the rank of CP minus 1 K0. All right. Actually, maybe I should put the label up here instead. Okay. And because of the fact that we're looking at the induced boundary map in the sense of relative chains, we know that these things sort of all get mapped to 0. So normally it's like there would be some sort of non-trivial thing, but because they correspond to chains in the thing you're quotienting by, we're going to set all of these to 0. Okay, so that's what it's like the boundary map looks like. It's like in the induced sense, even though it's like we're acting, it's like on the original case basis. All right. Okay. So that's set to 0, and then we have the part which we normally associate with the Smith normal form, which is this diagonal of 1s. Okay. And it turns out that this piece here then is going to be related to the relative homology. Okay. So this thing here is the rank of CP k comma k0, right? As you might expect. And this thing here is the rank of CP minus 1 k comma k0. All right. This piece here is the rank of the cycles, but the relative cycles, right? K comma k0. And then, let's try to extend it out here. This is going to be the rank of the boundaries, BP minus 1, k comma, the relative boundaries. Okay, so this is what's happening. It's like for the relative homology for k comma k0, and then I'm going to do the same thing now for L comma L0. Okay, so I'm going to draw a similar matrix here. All right, and then this is also going to be zeros, but this is going to be the rank of CP L0. This is going to be the rank of CP minus 1 L0. And then there's, again, this sort of Smith normal form part for the non-trivial part of the induced boundary map. Okay, and then this thing is going to be the rank of CP L comma L0, and then this is going to be the rank of CP minus 1 L comma L0. But of course the observation is that it's like this rank of CPL minus L0 and CPL L0 is the same as this, right? So because we've made the assumption that the L excluding L0 and K excluding K0 are the same set. Okay, so the point is that this piece, the non-trivial part, it's like of the induced boundary map is exactly the same dimension, and you can check we'll have the same form. Okay, so this is going to be the rank of ZP L comma L0. Then this piece is going to be the rank of CP minus 1 L comma L0. All right, so the bottom line again is that it's like this subblock, which is sort of the non-trivial part, which is relevant in computing the relative homologies, will be the same. It's like this block here, right? This sort of top part here will be different because in general, the rank of CPL0 will be different from the rank of CPK0. But again, it's like the part which is relevant for computing relative homology is exactly this piece here. And then by the assumption that L excluding L0 is equal to K excluding K0, this block has the same dimension as this block, and it's exactly the same thing. Okay, so that really sort of uses the things which we've learned. It's like from the Smith normal form but specialized in the case of the induced boundary map, which is appropriate for relative homology. So again, this sort of zeroes out this piece here, all right, and then it sort of allows you to establish exactly the excision theorem, which we discussed before. So let me just stop here for now. All right.